Good morning all. In this video, we'll see about a linear block code problem, how to generate the code word, and what is the error detection and correction capability of a linear block code. So first we'll see what is a parity check matrix. A parity check matrix is being denoted by H, which is used to check if a code word is a valid one, and this parity check matrix can be represented as H is equal to, it consists of a submatrix transpose followed by that identity matrix. And what is a submatrix transpose? How we can generate that one? So as I already know that in a generator matrix, it consists of a identity matrix with a submatrix, and the submatrix transpose can be found by writing the each column of a submatrix in a row wise will give the transpose of a submatrix. So from that we can generate what is a parity check matrix. Now let us see one problem. A parity check matrix of a particular 7,4 linear block code is given by H is equal to 1110, 1101 and 1011. This represents the submatrix transpose followed by that 100, 010 and 001 represent the identity matrix. So here we are asked to find generator matrix G and to generate all the code vectors, and what will be the minimum distance between the code vectors, and how many errors can be detected, and how many errors can be corrected using this code vector. So let us see a 7 comma 4 here. 7 represents n, the total code bits which are going to generate, and n is equal to 4 bits which represent the message bits. So the number of check bits q can be written as n minus k. 7 minus 4 will give 3. So with the 4 message bit, we are going to generate the 3 check bits, and if we add with that, that will give a total length of a code vector which you are going to generate. So the block length n will be equal to 2 power q minus 1. 2 power q is nothing but 3. So 2 power 3 will be 8 minus 1 is equal to 7. So which shows that the given code is a Hamming code, which is one of the condition for the Hamming code. So first we'll determine what is a submatrix from the parity check matrix. As I already mentioned, the parity check matrix, the first four columns of the parity check matrix is given by P11, P21, P31. So which shows a transpose of a submatrix. From the transpose, we are going to find what is the submatrix P. So H is equal to P transpose followed by that identity matrix is given. But P transpose is given by 1110, 1101, 1011. So from this we are going to write what is the submatrix. The submatrix can be written as, by interchanging the column and row we can get the submatrix. So here the first row of a P transpose can be written in a column wise for your submatrix. So 1110 can be written in terms of column wise as 1110, and 1101 can be written as 1101, and 1011 and 1011. This will give us submatrix. The second is we are going to obtain the generator matrix from the submatrix. So the generator matrix is given by identity matrix followed by a submatrix. So identity matrix for this is given by 4 by 4. So 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 1, and followed by that we are going to write what is the submatrix 1110, 1101 and 1001. So by means of a transpose submatrix we are finding what is submatrix, and from the submatrix we are going to obtain what is the generator matrix for a code vector. So once the generator matrix has been obtained, we can find what is the code words. The code word is given by the formula C is equal to M into P, where M is the number of message bits and P is the submatrix. So here C1, C2, C3. The check bits which you are going to generate here is only 3. It is because as I already got the equation Q is equal to 3. So C1, C2, C3 will be equal to message bit M1, M2, M3 and M4. Because K takes a value 4, so 4 message bits. Followed by that we are having a submatrix which given by 4 by 3 submatrix. So from the equation we got the check matrix C1. Check bit C1 is given by M1 modulo to added with M2 modulo to added with M3, and C2 we obtained as M1 modulo with M2 modulo with M4, and C3 will be M1 modulo with M3 modulo with M4. So with the help of this equation we can generate the check bits for the 16 message vectors. So why we got a 16 here? Because since the n takes the value 7, so 2 power k, 2 power k. So k takes the value 4. So 2 power 4 will be given by 16. So we'll be getting a 16 message vectors for this problem. So for the 16th message vector, we are going to generate our check bits using the formula C1, C2 and C3. Now let us take any one of a message bit and we'll see how a check bit has been generated. Let us take the fourth one, 0011. So for the 0011 message bit, how the check bit C1 is generated. What is the check bit C1? C1 is given by M1 modulo with M2 modulo with M3. So M1, M2 and M3. So 00 will give 0, 01 will give 1. So C1 is given by 1. So next, how a check bit 2 will be generated. A check bit 2 will be given by M1, M2 and M4. So M1, M2, 0, 0 again 0, and this 0 again modulo to added with 1, M4. So 0, 1 will give a 1. So check bit 2 is given by 1. And likewise, what is the check bit 3? The C3 is given by M1, M3 and M4. So M1, M1, M3. So 0, 1 is 1. And again 1, 1 will give a 0. So likewise, using these three formulas, we can generate a check bits for a 16 combination of our message vectors. So from this, we can write a complete code vector as M1, M2, M3, M4. Followed by that, we'll have a check bits as G1, C2 and C3. So the n bit length will be, the block length here will be 7 bits. 4 message bit with followed by 3 check bits. So for a 16 combination of a message vector, we got 16 combinations of our code vectors. From the code vectors, we'll find what is the weight of a code vector. The weight of the code vectors can be represented as a number of non-zero presence vectors, that is bits present in the code. So if you take the first one, all zeros, so number of ones is 0. For the second code vector, there are 3 ones are present, non-zero numbers or 1, 1, 1. So the weight of the code vector is given by 3. And the third one, we are having 3 ones, so the weight is given by 3. The fourth code vector, we have 4 ones, so the weight of the fourth code vector will be 4. Okay, likewise, we are going to find what is the weight of our code vector. Next, minimum distance between two code vectors. So how will we find a minimum distance between our two code vectors? So here, as I already mentioned, 2 power k, 2 power 8 will give us 16 code vectors along with their weight. So the smallest weight of any non-zero code vector will give what is the minimum distance. So if we see in our problem, the weight of the code vector, what is the minimum code vector, non-zero code vector we got here is number 3. So from this, it is clear that the minimum distance between the code vector, that is d minimum, takes the value 3 here. So next one, last, we are going to find what is the error correction and detection capability of a code vector 7, 4 linear block code. So here we obtain d minimum is equal to 3. So to find how many codes or how many errors can be detected, it's given by the formula. A d minimum will be greater than or equal to s plus 1. S is called as a syndrome, which is used to find how many errors can be detected. So d minimum is greater than or equal to s plus 1. D minimum takes a value 3 for this problem. So 3 will be greater than or equal to s plus 1. If I bring the 1 to the other end, so your s will become less than or equal to 2. So from this, it is clear that 2 errors can be detected using this method. And second, we are going to find what is the number of errors can be corrected. So it's given by the formula d minimum is greater than or equal to 2t plus 1. D minimum takes the value 3. We bring 1 on the other end. Here t must come here. So t will be less than or equal to, sorry, 2t plus 1. 2t plus 1. 2 comes over here. So 3 minus 1, it will become 2 here. So t takes a value less than or equal to 1. So from this, it is clear that one error can be corrected for this 7, 4 linear block codes. Okay, learners, we'll see similar problems in our next class. Thank you.